Hey guys, this is video 1 of 2 on section 16.6, which is surfaces and their areas. Heads up, this video is going to be focusing mostly on developing the idea of surfaces, and then the next video will worry about things like surface area. But at any rate, to start out this section, I wanted to reiterate a point I've mentioned numerous times throughout this class, that Calculus 3 is by and large meant to help us take our old calculus concepts and pop them up a dimension. Now, we've just been working fairly recently on line integrals, so being able to work with parameterizations of curves, integrate over those, depending on what you're looking for, we can find things like arc length of those curves. If I wanted to raise that up a dimension, well, we could be looking at something like surfaces and surface area. Now, to do this, let's think about the ways that we've approached plane curves before we worry about approaching this area problem. Okay, I want to point out that we've defined or we've used plane curves primarily in 3 ways. Okay, the 3 ways that we're used to encountering these things. First off, explicit functions. If I give you something of the form y equals f of x, I've defined y explicitly as a function of x. We're hopefully pretty familiar from Calculus 1 and Calculus 2. If you go to graph something that looks like this, you get a 2-dimensional plane curve. So if you're living in the xy plane, this is a curve. We've also seen curves that maybe aren't necessarily explicitly defined. Sometimes these things are implicitly defined. Well, what these things are going to look like is just going to be some sort of equation where I've got a bunch of x's and y's jumbled together. Not necessarily with my y by itself on one side. Now, if this is kind of vague for you, I'll give you guys an example. If I say something like x squared plus y squared equals 1, I have not explicitly stated this as a y equals f of x curve, but we hopefully all recognize that when you graph this thing, it is indeed a curve. You get the unit circle here. Now, note that implicit functions maybe aren't necessarily functions in the traditional sense. This thing isn't going to pass the vertical line test, but it does still describe a curve in the plane. Okay, so we're going to go ahead and count that. And then finally, a thing that we've kind of focused on in this class, we can also represent plane curves parametrically. Now, you can kind of view a couple different ways, to approach these parameterizations. We've frequently been working with parameterizations of curves that'll take on this form, something like x of t, y of t, and a vector. This is the vector form equation for, parameterization of some plane curve. If you have endpoints to this thing, maybe you would specify an interval where this works or where this thing lives. Or alternatively, if you wanted to maybe emphasize what was going on component by component, you could state this in parametric form. I could look at this like x equals some function x of t, y equals some function y of t, and phrase it that way instead of a vector. Either way, we've got a way to parametrically represent my curve. The way that we've approached this is thinking about plugging in a time and then having that time spit out a location that was actually on the curve. Okay, so plug in a time, spit out a point. Now, those 3 ways that we have approached my surfaces, or I guess my lines or my curves, and their representations, explicit, implicit, and parametric, these are ways that we can also represent surfaces when I see them in R3. Okay, if I want a representation of a surface in R3, we've seen that thus far. We're now dealing with an extra variable since we're in R3, so usually I would see something that looks like z equals f of xy. Okay? Again, the way that we interpret this, when you go to graph this is indeed a surface and no longer a curve, because we think about plugging in a point, okay, 2D point, x coordinate, y coordinate, and this is going to give us a location laterally that when you plug it into the function and it spits out a scalar, we interpret the z value as kind of like a height at that lateral location. So in that sense, when you plot all those points, you get your surface back. This isn't the only type of equation that we can use to express surfaces. If you want implicit surfaces, we have seen some of those too. Very similarly, this is going to be some sort of equation with a bunch of x's, y's, and z's mixed together, okay? Not necessarily with a z on the side by itself on the left-hand side of an equation, separated from the x's and y's. We don't necessarily need that. They can be all mixed together. Again, if you want an example, I'll fall back to one of the more basic ones. My sphere equation. My sphere equation is an example of an implicitly defined, an implicit function that defines a surface, okay? Now this last one, we actually don't have information on that yet, right? We haven't talked about it yet, so that's kind of the point of this section. And the reason that we want to talk about these parameterizations is they're kind of going to be important for us to figure out integrals that we're later going to be working on with these last few sections that we're going over. To really narrow in this parallel, when we were doing line integrals, and go to simplify a line integral so we can actually evaluate it, the first line of attack that we had for evaluating line integrals was fixing my bounds, my function, and my differential. And doing all of that required a parameterization for whatever curve I was looking at. Now, later on, if I'm going to be developing integrals that involve surfaces, you had better believe that those things are going to involve simplifying my bounds and my function and my differential into something that I can work with more readily. And that's going to call for me needing to know how to parameterize a surface. So, how do we do this? Okay, I'm going to go ahead and give you guys a definition here of what I mean and kind of what this is roughly going to look like. When we go to parameterize my surfaces, you notice a slight difference. Instead of having r of t, now I've got r being a function of two variables. Okay, and since this is a surface, I'm assuming I'm in R3, that means 3D points. Okay, so any parameterization you're talking about for a surface, we're going to plug in a 2D coordinate and get back a 3D coordinate. Okay, so note that I'm calling this a vector valued function. It's not a vector field because the dimensions of these things are different, but we do have a vector valued function here. And when you look at those individual component functions, I've got an x component, a y component, and a z component that are all functions of those two variables. Those are going to spit out the coordinates for the points on my surface, okay? So basically, the idea here is I'm plugging in some sort of UV point that's from some domain D or this region D. That's a 2D thing. I plug it into my function, and I get back a 3D point, which is going to actually lie on my surface being S here, okay? And, minor point of detail here, if you're worried about, vectors versus points, because, vectors are slightly different objects from these, we're just going to kind of let a correspondence be drawn between the result of this vector function, because this is spitting out vectors, and the points that lie on the surface. Okay, so if you plug something into R and you get some XYZ back, assume that the XYZ vector that you get back, that's going to correspond to an XYZ point on your surface. Now, with all of that out of the way, this is maybe still very abstract, like what exactly is going on in the background here. I'll try and see if I can draw a little bit of a picture for you here to demonstrate what mechanics are really going on in this definition. I said that we're starting out with some sort of a 2D space. So here's my UV space, okay? And then this function, okay, this parameterization, R, where you plug in UV and you get an XYZ coordinate back, this is going to, dump me somewhere in 3 space, right? Now, what's happening is this. You have to start out with some sort of a region D here. It doesn't necessarily need to be a rectangle, but for sake of my drawing not being too difficult, I'll start off with a rectangle here. And what's going to happen is every single point that is inside of this domain D, this is going to correspond to a point on my surface. Okay, so maybe you can imagine that I could have some sort of like, squiggly looking three-dimensional, no longer two-dimensional, a three-dimensional surface here. This guy being S. And what's really happening is, again, every single point that was in your D, two-dimensional D set to begin with, this is going to correspond to a point that is somewhere on your surface S. So, this little point that I've marked here, that probably corresponds to something like this guy over here. And if you want to think of a way to visualize this, this function R is really recording how we pick up this region D and stretch and distort it and squish it to form this surface that we're getting S. Okay, so R is just kind of algebraically informing me, if I have some sort of point in this D space, where does that correspond to this surface, in this S space over here? That's how we're determining a surface. Now, as far as actually parameterizing stuff, right? I'd mentioned that we have those three kinds of ways that we're used to looking at surfaces and looking at curves. Explicit, implicit, and the parameterization. We've already dealt with explicit and implicit surfaces before. We've cataloged names for some of them. We've already talked about kind of the setup that I have here, where if I have this function like z equals f of x, y, if I have an explicit function, maybe I might expect that a graph could look like this. If I'm given one of those functions that represents a surface, or one of those equations that represents a surface, how can I take that explicit equation and turn it into something that looks more like all this stuff up here, right? So, we kind of know what we're doing when we see z equals f of x, y, but how do I change that into an R? Well, we'll try an example really quickly. A parameterization of explicitly defined surfaces. Here's an explicitly defined surface right here. I just want to find a parameterization, any parameterization of this surface, z equals cosine of xy plus 5. Now, this trick here is obviously not the official name for it, but kind of what I like to think of it as is this is kind of the cheap way to parameterize a surface. So my cheap parameterization, the fast, easy, quick way to do an explicitly defined surface is going to be this. What I want you guys to consider is all of those points on a surface, okay, a three-dimensional surface S, these are all going to look a lot like X, Y, Z, given as a triplet, of numbers together in an ordered triple. Okay, so this is my point on my three-dimensional surface. Well, here I've given you guys what z is, right? So my next step could be, think about what happens if I substitute in that z. Well, if I do that, this is really x, y, and then cosine of xy plus 5. And now if I want to put this in a parameterization, r of uv, basically just replace some of your variables. You notice that we got this down from a point that required 3 variables to represent to now it's an expression that only requires 2 variables to represent, right? So I'm just going to replace x with u, and I'm going to replace y with v. for my curve parameterization, or surface parameterization. So if I want my R of uv, well, we just said x is going to get replaced with u, y is going to get replaced with v, x again is going to get replaced with u, and y with v. And here is my cheapo surface parameterization right here. Okay, that was really all that we needed to do. And I know that maybe you might be wondering, like, why is it necessary that I have to use a different variable? You know, this seems kind of silly that, like, I'm changing it just because. A parallel that I do want to draw is if we were thinking about our line integrals and substituting in curve parameterizations to deal with those, you notice that we worked with r of t most of the time and never something like r of x, even though our curves, you know, frequently had x components and y components. The main reason that we're going to work in this different variable here is later on when we run into working with integrals and we have to fix our bounds and our function and yada yada yada, most of the time that's going to involve a substitution into an expression that already has x's, y's, and z's in it. So we don't want to conflate our variables and mix those up. We're going to use distinct variables from x, y, and z whenever you guys give one of these parameterizations here. Now, they don't necessarily have to be u and v. You could be using other stuff, but I would highly recommend give your parameterization not in terms of x, y, and z. You're probably going to already be seeing those variables elsewhere. Okay? Case in point, I'll give you an example here. Sometimes we get multiple parameterizations back for surfaces. And, you know, here's kind of a case where there's a natural reason for why we might not necessarily use u and v all the time. Okay? In this particular example, if I want to parameterize this cone, okay, and here I'm giving you a specific chunk of the cone to parameterize. When I go to actually draw this thing out and think about what portion of cone I want, well, I'm making the restriction that this thing only gets to be 1 unit tall. Okay, so I'm not letting the curve actually continue off here. This is not an infinite surface. I just kind of want this little round chunk at the base of the cone. So, if I want to parameterize this thing, if I want to do my cheap parameterization, kind of like I did before, well, I could use r of u and v. And we said that if you think about x, y, and z as your coordinates, you replace x with u. If we're thinking about x, y, and z as my coordinates, we replace y with v. If I'm thinking about x, y, and z as my coordinates, I think about replacing that z on the end with the explicit function that I was given. But then when I replace that function with u's for x's and v's for y's, in this particular case, I would get something that looks like this. Okay, so u squared plus v squared. This is my parameterization, but I'm going to go ahead and point out the fact that here I can't just leave this be as is and go. I did give a restriction on what part of the cone that I wanted. You know, I can't just willy-nilly plug any old UV in here. I might get something that's where Z is bigger than 1. So I do have to restrict this down a little bit. What are your restrictions on U and V here? Well, my restrictions on U and V are going to be the same thing as the restrictions on X and Y. Hopefully that makes sense because we just substituted those variables out. So we'll go ahead and note, we basically want, okay, my similar restriction on U and V to X and Y. And if I think about those restrictions, well, just looking at this graph, we have a limited collection of X, Y values that we can actually use for this cone. You know, if you think about this thing casting a shadow, which of these x, y coordinates correspond to actual points that are directly above them on this cone? Well, let's think about putting these bits of information together. Okay, we are told that we wanted this cone, you know, z equals the square root expression, to have this restriction that z has to be stuck between 0 and 1. Okay, now notice if z has to be stuck between those things, that means this expression has to be stuck between 0 and 1. Okay, so the restrictions that I'm really facing here on x and y, I'm really going to reference that, you know, square root of x squared plus y squared, this has to be stuck between 0 and 1. Now, comment, since this is a square root function, it's not going to spit out negatives anyway. You don't necessarily have to explicitly spell out that beginning part. So here, if you wanted to make those restrictions on x and y, we just said we're doing the same restrictions on u and v. Okay, so I could also say that I'm using this parameterization. I'm just going to copy this thing over here. I'm not doing anything really fancy with it. I could use this parameterization where that square root expression, you know, u squared plus v squared square rooted, where that guy is less than 1. Okay, so this would be one way I can get my parameterization taken care of. Or an alternate method, because I did hint up here multiple parameterizations might be possible. Another way that I could think about this is, you'll notice it's a round region, and I've got all these squares and square roots popping up. If I wanted an alternate way to think about this that might actually be really useful potentially in an integral, an alternate method is we could think about some of the other coordinate systems that we've been using, right? So I could consider my alternate coordinate systems kind of like polar or cylindrical here. Now, since this is really just two variables, it's more polar than cylindrical. You know, we had these coordinate conversions, you know, x was supposed to be equal to r cosine theta, y was supposed to be equal to r sine theta. We also had a potential conversion that x squared plus y squared, this should really give you r squared. What I want you to go ahead and do is think about making a transition of this expression, okay, for our parameterization, but let's see if we can use conversions that are a little bit more fitting for polar. Okay, so let's maybe try, you know, let's go ahead and convert this expression, just u v root u squared plus v squared. Let's see if we change this up a little bit, okay? Now, when I do this, I'll get a different parameterization here, so let me maybe label these. This was my R1 parameterization. I'm going to give you a totally different function here, so I'm going to call this R2. Once we do this conversion, this thing is going to be a function of r and of theta, because we're trying to get rid of all of the u's and v's here. Now, if I try to get rid of u, this first bit here is going to suggest that u could be replaced by r cosine theta. If I wanted to get rid of my v, this second bit here suggests that v could be replaced with r sine theta. And over here, this x squared plus y squared, or, you know, u squared plus v squared, that suggests that this thing on the end could be replaced by square root of r squared, or we could just go ahead and simplify that here. We had the restriction that our z component had to be stuck between 0 and 1. I'm not worried about getting any weird negatives or anything like that back. So here I'm just gonna stick this with my r. Now notice I got a different function here to describe what's going on with my r's and thetas. That different function is going to call for a different restriction on your region D. Okay, so this restriction that I was giving here, this is me specifying what my potential input values are. Before, I just had to pick a u and v or an x or y that were inside of that unit circle. If you want to specify the same unit circle here as the values that you're plugging in, here we have different quantity or qualities for our polar coordinates. R refers to radius. If we want to be inside the unit circle, you're going to want an r that is stuck between 0 and 1. And then if you wanted to consider all the points inside the unit circle, you're going to be in all of the 4 quadrants. This means that we are considering thetas that are stuck between 0 and 2 pi. Okay, so here this is actually kind of a different approach to building this surface that we've got here, because you may notice that if we think about a D for this original parameterization, it's kind of like we're starting inside of the unit disk, and then we mush that unit disk upwards into our cone. Okay, so it's kind of like we nail down the center of the unit disk and then you just lift up the edges to form your cone. Versus here, there's kind of a different approach to taking your D region and mushing it around to form your surface, right? We're actually starting on something that looks a little bit like a rectangle in these polar coordinates, because one component is stuck between 0 and 1, and then the other component is stuck between 0 and 2 pi. So this looks like a rectangle. What's kind of happening here instead is it's a little bit like when we go to piece our cone together. If you think about the fact that, there's kind of this boundary here at 0 and 2 pi, think about maybe unrolling this cone. Okay, so if I do something like this here, so that ultimately you're going to get a region that looks kind of like that. What I'm going to go ahead and do is kind of stretch this guy out across the bottom. Okay, so this entire bottom edge really gets compressed down into a point. This is just a different way for us to take our D region, or rectangle that we actually get here, and identify points on the rectangle to points on the cone. Okay, so instead of that lift and stretch method that we had for taking the disk to the cone, we're still taking a 2D object and kind of mushing it around to get this 3-dimensional surface back. Okay, so do note, different parameterizations, you can still refer to the same surface. Your functions are just potentially going to look different, and you might have different regions that you're starting out applying that parameterization on. Okay, now other comments on these alternate parameterizations or working with alternate coordinate systems. Sometimes the alternate parameterizations are really useful. Hopefully we could kind of see in that last example, if I was dealing with a round region, we've seen numerous times before that round things frequently cause problems. If you try and stay in Cartesian, you get a lot of square roots and weird things like that. Another reason that maybe you might want a different coordinate system, I'll try and highlight with this example. Let's say that I want a parameterization for the unit sphere. Now, if I try to do this the cheap way, right, the cheap parameterization. The cheap parameterization kind of calls for this to be written in an explicit form first, so I'm going to go ahead and solve for z. If you do that, you're going to get square root of 1 minus x squared minus y squared, but not just the square root, you also get the negative version of it too. Okay, so you could potentially get, a cheap version of your parameterization where you look at, something of the form u, comma, v, comma, if I just wanted to replace this, with u's and v's, big red flag here, this is actually not a function, right? The way that functions work are if you plug in a unique point, you are supposed to get some sort of singular output back. This is suggesting I plug in a point and I might get one of two things. Now, the reason for that is this. If you wanted to think about there as being a sphere in, 3 space, this guy doesn't exactly pass the vertical line test, right? Any point that I've got up here, if you drop a vertical line through, there's a corresponding point that is immediately below it. So, if I just had the top half of the sphere, that would totally be a function. If I just had the bottom half of the sphere, that would totally be a function. You would actually need 2 parameterizations for this surface with this technique, okay? So with this trick. Now, an alternate way that I would suggest that we consider this instead, especially since it's a sphere and we do have a spherical coordinate system, is let's actually try to do this in spherical, okay? Now, this sounds really messy, but I promise it's not too much worse than just remembering your coordinate conversions for spherical, right? I'm going to go ahead and make the observation on your sphere. We basically have points that look like, and this is totally crazy, s comma y comma z. Okay? Maybe a little bit of a letdown there. But every single one of those points that's on the sphere, since this thing started out being basically radius 1 here, I'm going to go ahead and make note all of my points, they're 1 unit away from the origin. Okay? Okay, but I'll go ahead and make the note, but these points are 1 unit from the origin. Now, a refresher on my conversions for how to do spherical, we have said before that if you want to convert x is going to look like rho sine phi cosine theta. If you want to convert y, this is going to look like rho sine phi sine theta. If you want to convert z, this is going to look like rho cosine of phi. Now, you'll notice that there are 3 variables in this. If I'm doing a parameterization, I want to cut this down to just 2. A trick that I can go ahead and use to represent the sphere is, since I said that I wanted all of my points to be 1 unit away from the origin, I really want my rho, which is my distance from the origin, to be 1. Okay, so since I want these things all 1 unit away from the origin, I'm just going to use my conversion formulas with rho equals 1 subbed in. Okay, that's really, going to be it for the most part, right? So if I try to do this, you'll notice the variables that I'm using, they're in terms of theta and phi. Well, if I wanted to have an x coordinate, we said we wanted to replace x with this conversion formula, but use rho equals 1. That means my first slot is going to be sine phi cosine theta. If I want to replace my y coordinate with my y conversion, but make rho 1, this is going to be sine phi sine theta. And if I do the same thing on this last component, I'm going to get a cosine of phi here. Now, if you want to restrict down to, what's the smallest domain that's going to be required, to actually express the entirety of your sphere, think about the way that our spherical conversions worked. You know, what values of theta do you need to make it all the way around the sphere? Well, here I'll go ahead and note the restrictions on theta. That needs to be stuck between 0 and 2 pi. And if you're worried about your restrictions on phi, that was supposed to be the angle where you come down off of the positive z-axis. Unless you want to start overlapping or things like that, well, we're just going to stick that guy, that phi, between 0 and pi. And that'll give you the whole sphere back. Okay, so I didn't have to worry about like solving for z or, you know, doing anything like that, getting my 2 pieces of my parameterization. So I can use this guy. Let's actually differentiate these 2 functions. I can use this guy instead. Okay, and you'll notice 1 function. I don't need 2 equations to express this thing. I've just got 1 surface that I'm dealing with, and I don't have to break it up in pieces. Now, with that said, we've been doing a lot of this work on taking explicit functions and turning these into parameterizations. I'm going to switch gears a little bit and think about going the other direction. You know, how do I know what a surface looks like if I give you a parameterization for it first? Well, we'll start out with the easy question to answer here. If you see something that looks like it's in this form, keep in mind, if you see something that looks like u comma v comma a function of u and v, this is our cheap parameterization right here. So do be able to recognize this guy when you see it in either form. This is going to be the same exact thing as my surface z equals f of x, y, right? So kind of what we're doing here is think about it this way. If you want to, you know, kind of deconstruct this, I have an x component. X looks like u, right? So I basically have x equaling u. I have a y component, y equals v. I have a z component, this z equals f of uv. If you make the appropriate substitutions here, we're basically getting z equals f of xy back. Okay, so if you see something specifically in this form, okay, a u, a v, and then a function of u and v, instead of swapping x and y for u and v, we're doing the opposite. We're swapping u and v for x and y. So here, if I wanted to do kind of the same trick, you know, deconstruct this just like I did before, again, I have an x component that is u, I have a y component that is v, I have a z component that is u squared plus v squared, and if I make the appropriate substitutions, this is going to suggest that the surface that I've got is really z equals x squared plus y squared. Okay, and hopefully we recognize that, you know, this is a surface that we've actually played around with before. This is a paraboloid, okay? This is that paraboloid with that nose, you know, touching down at the origin. Now, if you want a different approach, let's say you don't necessarily have u and v written in this format, but here we'll try the same example again just to highlight how this works. For simple surface, you know, maybe we might want to consider, you know, if I just have absolutely no clue how to do this, if substitution looks a little bit messy, what can I try to get a feel for what the surface looks like? We can use the same technique to kind of what we did with level curves of surfaces to get a feel for what a surface looks like by setting something constant. I can do the same thing here. You know, if you wanted to pick one of these parameters, either u or v, doesn't matter, you can do this one at a time. If you want to pick one of the parameters and set it constant, what that's going to give you is then a parameterization that only appears to have one variable in it, and that'll look a lot like a curve. We've seen that, you know, if you have r of t, just the one variable t, that thing looks like a curve when you graph it. So the idea is this. If you do that process where you pick one of the variables, set it equal to a constant, draw the curve, try a different constant, draw that curve, try a different constant, draw that curve, you're getting a bunch of grid lines that'll kind of tell you what the shape of your surface is, right? So here, I'll give you kind of an example. Let's say that I wanted to set my y component constant. What this is really going to have me do is let's set my v constant here, right? So pick one of your parameters, pick this y component, pick that v. I'll set that equal to a constant. What this is going to look like is this. I will now get r of u k. Okay, so this will look like u, some number here, k squared plus v squared. And how I now want to think about that is this. You don't necessarily have to do this for an arbitrary k. You could maybe make like a table of different parameters here. So I could do something like, r of u0. This would turn into u0 v squared. If I wanted to do something like r of u1, this would turn into u1, 1 plus, why am I doing the v here? I should be keeping the u. Sorry about getting this backwards, guys. So 1 plus u squared. And the way to think about drawing that, if I wanted to, pair these things together, I'll go ahead and do one more of these. Get u2, 4 plus u squared. If I want to draw all of these on the same graph, think about it like this. For this first one, I've basically got a 0 in my y component. So since I have a 0 in my y component, that means that this thing is just totally going to lie in the xz plane, right? So if this thing is totally lying in the xz plane, that means that if you pick some sort of value for u, or your x here, once you plug that into u squared, it'll tell you how high to go up for the z component, right? So if I plug in 0 for x or u, that means I get 0 back for u squared or z. If I were to plug in 1 for u or x, I would get back 1 for u squared or z. Same deal if I plug in -1. And, we could hopefully recognize here, if I try other points, like if you plug in 2, you get 4 back. Once you track all these, that first curve is just going to be a parabola. Now, we can do the same exact trick for this second curve, except for I'll kind of shorten this process up a little bit. Rather than going point by point, I'll make the observation that we've just got some shifts going around here. The fact that you no longer have a y component of 0, you have a y component of 1, means that wherever your curve is, it's actually going to be on this plane y equals 1. So think about the plane that's pushed out a unit forward. And then the z component just has a shift upward of 1 unit. So it kind of looks like we've got a parabola that's got a 1 unit shift upward on this y equals 1 plane. And kind of a similar deal over here for this third curve. We are really on the y equals 2 plane, so we're even further forward. And this time we have a 4 unit shift upward. So I'm going to get probably like this parabola right here. Now notice, if I have all of these grid lines, if I wanted to draw even more of these curves, what's really being suggested by these grid lines is the exact paraboloid that we knew that we were going to get from this expression above, right? This is the same curve that we got back up here, okay? The z equals x squared plus y squared. So the whole idea of my grid lines is, when you're drawing your grid lines, you're really getting cross-sectional slices for this particular curve. okay? Now, if that's maybe a little bit of hassle, and to some extent, potentially is, we do have graphing utilities for a reason. You could potentially ask a computer to plot a parametric curve instead of trying to do this from scratch. What if maybe I just want an algebraic approach for doing this? We can also piece together these parametric surfaces using algebra. Now, the way that I want to think about this is, does the parametric equation that you're given, does this suggest any sort of equation that can link your x, y, and z components? Right? And you notice here, I don't quite have the cheap parameterization going on. I don't have u comma v comma function of u and v, so this will look a little bit different. What I really want to do here is, again, think about the fact that each of those components is supposed to be represented by x, y, and z, or rather, those are the components that are standing in for each of those functions. So, is there any way that I can try to link together, if x is equal to u cubed plus v, and y is equal to u, and z is equal to v, is there any way that I can kind of substitute these together so I completely get rid of my u's and my v's and I just have x's, y's, and z's left? Well, in this particular case, the substitution is actually pretty straightforward. If I replace u with y, and if I replace v with z, this is going to give me an equation of the form x equals y cubed plus z. And this is actually going to be the surface that you would want here. Okay, if you want this in the form z equals f of x, y instead, well, for my more final answer, you probably just want to solve for z here. You'll get x minus y cubed. Okay, so this surface, if you want this in a more standard form, think about how you can connect together your x, y, and z components. What substitutions can you make? Are there identities that you can use that'll let you group these things together if they're not already obviously grouped together in a way? Think about what you can do to link those together. Now, the reason that I bring in identities, I'll give you one more example of these where we try to find the surface from the parameterization. Let's see if we can find this one. Okay? Again, I'm trying to draw this parallel here of my x, my y, and my z. Now, if I just write these out, x equals cosine u, y equals v, z equals sine u, there's not a lot of substituting I can do. Right? There's no v in any of these other equations for me to stick my y in. I can't swap out my sine u and cosine u. They're different functions, so they aren't equal to each other. So this is why I said try an identity, right? We do have a couple trig identities that are kind of things that stand alone and involve the way that sine and cosine connect to each other. And maybe we could use one of those identities to start subbing stuff into that instead of, an equation that we started with already, right? So, for example, this is the popular one that everybody likes. If you take sine squared of pretty much any variable here, and you add it to cosine squared of the same variable, we all know that we expect to get 1 back. Now, if I actually tried my substitution here, okay, what this is going to suggest for me is that z squared plus my x squared, this is going to equal 1. So this is actually the surface that I'm looking for if you are worried about the fact that this doesn't have any y representation here. I'm going to point out the following. When we said y is v, usually that's kind of the filler that we use for y anyway. This is almost kind of like saying, hey, y is just y. Really what this does is, since it's not really related directly to what's going on with the x or z components, we don't see any v's over here. There really aren't any restrictions on y for this particular parameterization. You know, if you want to plug in a particular v value, you can go ahead and do it. There's really no, you know, restrictions or rules on that here. Just, you know, whatever number you pick for v, that goes in for your second component. So what that means is your y component here is basically totally arbitrary. And that actually lines up very well with picking this guy as my surface, because if y gets to be arbitrary, that totally fits in here. You know, there's no slot for y to go in. You know, that means y can pretty much be anything, and hopefully that makes sense because we've classified surfaces like this as a cylinder, right? If you have an equation in, you know, three-dimensional space that you're taking this thing to live in, and it's only got two variables, this thing is a cylinder. And the way that that worked is whatever two variables you have, here it's x and z, think about the xz plane and what sort of two-dimensional curve you would graph here. Well, you know, if I'm thinking about my xz plane, this thing looks like a circle, but we've just said, since y doesn't show up, y can pretty much do whatever it wants. We're going to get a extruded shape along the y-axis because of that, because if I set y to do whatever it wants, I can draw the circle pretty much anywhere, right? So I will get my cylinder back, and the fact that I didn't have anything to replace y with, that was totally fine. Okay, so again, the big idea here, see if you can link your variables using some sort of an equation. If you don't directly have one that you can start substituting stuff into, see if you have other identities that can help you out.